Almost everybody. Okay, I wasn't kidding, 9 o'clock sharp, so let's get into it. We're going to start today with a presentation from Pablo about forecasting 2.0. So please welcome Pablo.
So, hello everyone, and thank you for coming. My name. So, should I get my slides?
Oh, well, there you go.
Yeah, so the title of this talk is Forecasting 2.0, and this is, of course, a reference to, I think, Andre Tarpat, one AI, legendary AI researcher that introduced an infamous blog post a few years ago about for programming 2.0. Like now you go from writing code to giving examples and the code is weights in a neural network, right? So this is a reference to that, but in forecasting. So let me just ground us and imagine like the typical forecasting or time series analysis process. You create a model. I forgot to include the data, but you feed the model and importantly, then you can, depending if you are a statistician or not, you will check the coefficients and the some diagnostics plots, hypothesis test, etc., and then you can get a forecast. Right? So I'm going to start with something that sometimes I might presume that we don't care much about, which is the method that we are using to estimate our model, right? So we can do several things, several algorithms that map from data to the model coefficients. So I would say that maybe we care more depending on if we want to squeeze a bit more performance, etc., depending on the context. But basically the idea is, okay, so we are running these algorithms to estimate our models. Can we do better than the one that we currently have? So what I'm going to present finally after years of thinking about this, we're settling into some concept of the neural estimators or artificial intelligence estimators or whatever. And the process for getting these estimators is basically based on simulation. So we have a model or a time series process. We can simulate the model coefficients. Then we simulate the time series, and then we have the observed time series virtually or synthetically, and the true underlying the ground truth for the time series, either the model coefficients, but we can also compute the ground truth for the forecast. And the neural network learns to map from the observed part of the time series to the ground truth, either the coefficients or forecast or other properties of the time series that we are interested in. And the way we do it, we simulate many time series, and we expose this neural network. We train this network to map from time series to coefficients. And once we train the neural network, then we stop training, and this neural network, when we run it in a pre-trained model on new time series, it will be basically a statistical estimator, a neural statistical estimator. And the thing that we can do with this neural network is that we can actually use it to approximate optimality for a wide range of criteria, right? So optimality could be prediction error, that's mean square error, but it could be something like remove the bias also of the estimators that we will see if this is useful or not. And I'm going to start with some claims. For example, is that these neural estimators, even of simple time series processes like exponential smoothing, additive components, they can already deliver impressive performance, right? So if we substitute maximum likelihood for these neural estimators, it can give very good performance. And then we can also use this to approximately, so quote, solve estimation problems that are hard or difficult to solve, such as the estimator of a very humble, the beautiful AR P class of time series models. Right? So we don't have unbiased estimators in general for that class. It's an open problem. We will see a little bit more about that. So we will start with some results. So that's in media res, I think is the term Latin. Let's see so this illustrates most of the points in the methodology of what I'm talking about. So imagine that the universe is just simple exponential smoothing. So the game that we are playing is we want to find good estimators for the alpha. We would say also there is the L0, the starting state, that we should be estimating, but let's ignore that for a while. And let's focus on this. This kind of gives you the full picture of the performance of an estimator. So on the x-axis, we have the true value of the alpha for exponential smoothing. And on the y-axis, we have the error that an estimator would make for that value of the parameter. Now, on average, we have Gaussian innovations. The line in magenta is the Kramer-Rao bound. So it's basically, if you want an unbiased estimator, you're going to be below that line. Usually, it doesn't mean that. So in some processes, you can basically approximate it, but sometimes you cannot. You cannot even get close to that. If you allow for bias, then you can go below this line. This is kind of a idea of optimality. And what we have here in blue is simple exponential smoothing with a maximum likelihood estimator. And we can see that more error usually is not good. And so basically, one of the observations here that summarizing the neural network that has been trained with simulating from the alpha parameter uniformly, it tends to work, has much better error in most of the parameter, most of the parameter space. But in this little corner, when alpha is close to 0, even maximum likelihood, in this case, it's better, right? So in these three estimators, right, in green is the bias, right? So it's a neural network that is approximating an unbiased estimator of the alpha for simple exponential smoothing, has paid, right, a huge cost in average error, averaging across the alphas, but no estimator dominates the other for the full parameter space, right? So we are always in a trade-off, right? So I'm not telling you magic. In some cases, you can do magic, but in most cases, for example, maximum likelihood will work better than other estimators for some range of the parameter space. And then, of course, this does not mean that the one is better than the other also in general, because in your specific case, you could be just in this, in the close to 0 corner of the universe. And for that, even if you have thousands of time series, maximum likelihood will work better. But this is basically we can, right? So it will give you a picture of whatever we want to do. Let's imagine that with neural networks, we can try to approximate whatever trade-off could based on the values of parameters that we want. It's a bit hard to do, but the classical ones would be, well, minimize this error, but then like to penalize for the bias. This is a plot of the bias of these estimators, right? So we can see that maximum likelihood, in this case, it's a little bit unfair comparison, but qualitatively this holds, you can be a bit better, but basically this is the bias plot. Close to 0 is good. And we can see that the maximum likelihood has a negative bias, so it tends to find values of alpha smaller than the truth, when simple exponential smoothing is the true underlying process. And then the green line is the bias estimator that has strongly reduced the bias, also compared to the other neural network estimator, which is from the uniform simulation. Right? The neural uniform here, it's very similar. Conceptually, it's the same as a Bayesian estimator, right? So with a uniform prior, there can be a few differences, but we could say that it's an approximation of that. It can actually help in doing, the Bayesian posterior, the posterior mean in this case, but maybe faster, or it's easier to do in general prior distributions. But basically, this is the story, right? So then we could do a few more things. And the point here, well, basically the point of forecasting 2.0 is that I'm trying to do something that is some experiment, right? These are quite interesting, but let's imagine that I want to do this neural estimator for exponential smoothing AAA. So I need to simulate from all subsets or ETS, so basically with trend or no trend, seasonality, no seasonality, and then even some aspects of different periodicities for the seasonality of no periodicity for tweet. So you want to detect that, so it's not given to you like we tend to do in many cases, many packages. And then what we minimize for, and this may be some very interesting to some people here, for example, the horse working in the Adam package, that they have estimators that focus more than one step ahead forecaster. They want to approximate that in sample. But we can also do, we can take model selection as a classifier, and from simulations train a classifier that selects the best class. There is, of course, a lot of research done before in this space, before this idea. But very simple. We have no information on the parameter space. So alpha, beta, and gamma, we do priors, uniform priors, and we don't even restrict to these realistic constraints of beta between 0 and alpha, gamma between 0 and beta, etc. We can do crazy explosive processes. And basically what I want to say is that this is just, in a few lines of code, we can simulate from simple exponential smoothing processes. So simulation is basically trivial. And then the estimator is way, way harder, right? So we can do maximum likelihood, but then if we want to do something better, it becomes, let's say, more and more difficult as a tractability of this problem, right? And this is one of the results. So I'm expanding on results from this, I guess, celebrated paper from Rock here in 2002 about introducing the ETS. And in this paper, the authors explored the idea also of alternative estimator, right? So you have a minimum least squares. But then, for example, this one that I highlight here, AMC, is an estimator that minimizes in-sample prediction error from horizons 1 to 3. It's not the typical one step ahead estimator or minimization of minimum square error. And there is also model selection by AIC, if I read it correctly. And we have other estimators, for example, one that minimizes, if you want to minimize prediction percentage error, you can try to find the values of alpha, beta, and gamma, and the models that minimize them. And in this neural estimator for the model class that I introduced before, so very simple one, it gets a little bit of better performance, right? But then if you think about it, what I was doing for this neural network is that it's estimating, basically it's trying to find the estimator that minimizes prediction error for every of the 18 horizons in the M1 dataset per horizon. So you can think of a different estimator per horizon. Then model selection, instead of using AIC, which is great, it's one of the most important results in statistics, but have some problems, right? So in finite samples, we have some, it's not optimizing exactly for what you want, let's put it this way. But in this case, we can do some form of, well, I don't so much care about selection, just find whatever it's minimizing the prediction error. And it is not a completely fair comparison because I didn't put multiplicative effects, but we can put them. And also, across the whole competition, I'm using the M1 here. I guess you could say cherry picking is mostly because there are, in Ross paper, they show more estimators for kind of almost the same model class. So it's to be a more fair comparison. In terms of mean prediction percentage error, the performance is very good, but then we go to the median one and it's even better, right? So we have here the M1 participants, right? So we can see that this neural estimator is basically either, well, with the section of horizon 4, I guess, it's tying or outperforming other of the models that were applied. And then in terms of model selection, we can compare here whether you find a trend versus no trend model, and it is a bit more accurate, the neural network. This is in simulations, not in the M1, because In reality, we don't have the ground truth. It's like just a small problem. But, and so this is basically the idea. And I want to introduce another one that is a bit more exotic, but basically might be also the cause why I'm taking so many years to, finalize the paper. Because when we think in terms of estimators, we have like statistical science have provided, or statistical decision theory has provided more concepts of desirable estimators. One that is pretty interesting to me is the minimax estimator. So basically the minimax concept, if you like the theory, let's say that we are playing a game, I want to find an estimator, and nature wants to find a distribution over the true parameters of the process, and nature wants me to make the most error possible, and I want to have as small error as possible, and we can set that in an equilibrium, right? Because, for example, if nature wants to say, well, I see that your estimator is making the worst model when alpha in simple exponential is 1, so I will always produce alpha 1, but then I can play it again. I know that you are going to give me the universe is all alpha equals 1, so I just going to produce alpha 1 in my estimations and getting 0 error. So we play this game. Eventually, we settle in an equilibrium. That another interpretation is this an estimator that focuses on the worst case scenario. So I'm going to reduce the error for the worst case. Applications for that, it's a bit exotic because, well, we don't have in general estimators for the classic processes in this. While we don't even have unbiased estimators, so minimax is even maybe a bit more out there. But applications here, I look for some applications. There are some that I really understand and interiorize. The ones that I found recently very interesting, for example, in radars, what I guess I'm not so engineer or what is the signal processes is the problem of beamforming, which is basically trying to detect or maybe trying to accurately detect the position of objects that move very fast. So it has applications in work. So hopefully there's funding on that space. And but mostly in general, what people say is robustness, right? Because you want in a very loose definition of robustness. And then another one that I find very interesting in when you have adversarial reporting, right? So makes in mind that I am giving you the numbers for the time series. I know that you are going to make a forecast with a model, and I want to misreport slightly the numbers so you can make the forecast that I want, and you will make the decision that I want, etc. Or there are other scenarios like that, and then also in finance, right? You might want to not perform on average. You might want to be risk averse and say, well, I don't care much about benefit on average. I just don't want to make big losses, right? So what we have here in the plots is basically the inverse cumulative distribution function of the errors in the N3 data set. So it basically, I just put the plot on the left is just so we don't see much, but the plot on the right is the ratio of these error distribution functions. So basically, what we have is the error of the neural minimax divided by the error of the other estimator. So it's basically numbers greater than 1 means that the minimax estimator is worse. Smaller than 1, it is better. So I want you to focus here just on the blue line, which basically it's comparing the max estimator to maximum likelihood. So basically, for half of the data set of errors, the minimax estimator is worse. But when we start moving into the bigger errors in the error distribution, then the minimax is performing better and better. This is it's a very interesting problem, right? So just to open a little bit your mind of this, I believe these are things that after, I guess, this talk, relatively easy to do with a neural network, right? And very difficult to derive analytically, at least with my limited mathematical analysis capabilities. And now we go into the ARP class. This is just to motivate that I think it's important and pretty exciting. So ARP, let's put it this way. Maybe Rob can, or somebody else can correct me if I'm wrong, but I believe that the unbiased estimation for the ARP class, it's an open problem, maybe for more than 70 years, right? Because it's the idea, you have a correlation, or, well, whatever you estimate in the present autocorrelation, back in the day when people get out bias, you start thinking, well, we can try to capture an expression for the bias and then remove it from whatever least squares. But it becomes increasingly hard, especially when we increase the P, so the order of the ARP class. And then I'm going to also show some things like uniform calibration. So as you know, we estimate a model, we get some prediction intervals. These are usually not well calibrated. It's hard to include parameter uncertainty, model uncertainty, all of those things. And usually we have approximations to solve it, like with the bootstrap, etc. With this, we can also approximately solve it, maybe in a better way. And also another interesting problem that I'm going to show is simultaneous prediction bands. Right? So when you want the coverage for the full prediction path, not the marginal for each horizon. Anyway, the simulating ARP is also trivial, and we can simulate many per second, right? So this is not an scaling issue. It's another important point that I want to make. Applications for unbiased estimation. I would put two. I'm not an expert in any of those, but scientific experiments in the sense that you want to estimate some population parameters. And for example, the typical one that I imagine, well, two scenarios. When you have like a constant in an experiment with, treatment and control effects, but the errors or the measurements are correlated, you are interested in the constant, in the additive constant, not on the AR coefficients themselves. So you want an unbiased estimate for the constant, and then in econometrics, economics, the impulse response functions. So you want to estimate the coefficients and make some inference about the values. There are applications in biology, etc. And the idea for why don't you want bias here is if you do repeated experiments, every experiment, I just want to reduce estimation error or prediction error. But if everybody makes different experiments and all are biased in a way, we have a systemic risk in that, the principle of science, of, like repeating experiments, maybe errors canceling out, etc. It does not happen if everybody has a bias. And then in hierarchical forecasting, I'm also not up to date to the latest results, but from what I remember, some ideas in this space, like for reconciliation, assume bottom level unbiased, which we don't have. Right? As far as I know, I might be missing something here, but I'm not sure what would be the results of this, if there is any benefit, but anyway. I want to, in this overcrowded plot, it's similar to the one that I did for simple exponential smoothing, but for the AR5 class. So what we have in orange here is the neural estimator uniformly from ARP, which is along. What do I mean by uniformly sampling from ARP processes? It's not easy because we are constrained to stationary ARPs, etc. And then we have the bias, and then other estimators like the familiar ones, so maximum likelihood, ordinary least squares, Book, Jules-Walker, etc. And another thing that people tend to ignore is that this, for example, maximum likelihood, even though it's quite good, it's also numerically unstable. So if you simulate a million time series uniformly from the ARP stationary parameter space, 10% of those or more will give numerical errors. Right? So I have to fall back to the next best one. And this is for prediction error, and this is for bias. So we can see here that the bias is reduced for the green line, the bias estimator is not perfectly unbiased. It's way smaller than any of the other estimations for the bias. I'm just plotting here one of the parameters. And then I just want to use a particular parcel to this plot. So here is about calibration. Depending on the values of the parameter, the phi1 in this case for the AR5. In orange, it is the neural estimator was very good, but if you train, for example, with the pinball loss, you will get calibration on average. So basically, for the whole population of ARP processors or in your dataset, you check and, well, my P95 quantile is well calibrated. But this happens on average. But for every individual time series, let's put it in this way, it will not be calibrated. Something that this is, I would say, so sophisticated that it's difficult to be tested empirically. But at least I don't know exactly why. But we can actually try to reduce this, if you will, wall-to-wall bias in the calibration with the neural network, so we can reduce it a little bit. I could reduce it more, paying a small cost in prediction error. And in this plot, importantly, I cannot show the calibration of other estimators because it wouldn't even show in the plot. So bad in that sense. The trade-off here is quite good, but might not happen in general. But basically, it's also an interesting point that I want to make. I don't want to be on Bayesians but the idea of bias and here, because an unbiased estimator might not make sense in every situation, right? If you want to estimate a probability, to be unbiased, we need to produce negative probabilities in some processes. But in this case, it's an example of the bias. Well, on average, yeah, you get calibration, but for every individual time series, minus a few cases, it's not calibrated. And then finally, the simultaneous prediction bands. It's not something that is super important in the sense that if you can have prediction intervals, the point-wise prediction intervals, you can approximate the simultaneous prediction intervals. It's just that it can get extremely annoying, extremely computationally intensive to compute these prediction bands, the simultaneous prediction bands, because it relates to the joint distribution, the joint forecast distribution, not the marginals per horizon. And this will tend to overcover. I'm not sure I'm doing with time. But now we get into the more, so this was just mostly to motivate and give you maybe some dimensions of the things we can do with this idea of simulating, imposing some optimality criteria for the estimator, and then train a neural network to approximate these estimators. And then we got into the software aspect of it, of the abstraction. So I leave you here with a quote that I like about this English mathematician. This was before computer science existed. Basically, the advance of civilization follows how good our abstraction are, right? So what I want to make a point here is that with good software abstractions, it can give us way more power of analysis in a way. So this is the second leg of the idea. So we have now estimators for known processes, which is pretty interesting, right? Maybe as a statistician, it's very interesting to try to improve or what other people try to do before approximating the process. Very clear approximation. But I would say it's maybe on a personal level, it's even more powerful. The idea is what other model classes can we now create or define from first principle that will result in a very, very hard estimation problem, but that can now be solved by this neural approach. So because basically now model class becomes the limiting factor, right? So we are not limited to AR, ARMA, ARIMA, exponential smoothing. We can do many other things that would be hard to derive estimators. So some of you might cringe here, and I was coming to this workshop trying to get some ideas. I saw some ideas yesterday, and in France's talk, they have something similar to that. So what I want to present here is, what the way I'm thinking about that is that we want to define, properties of estimators. It's a whole different game, but just focus on models. Imagine that we can think of some nouns and verbs, or what are the objects that we are trying to work with. So for example, an object could be the innovation distribution. It could be, Gaussian innovations, whatever, binomial, and then we can compose distribution maybe with mixtures, maybe piecewise composition, etc. So we can create very sophisticated error distributions that would result in an estimation problem that it's hard to solve. But now we can approximately solve as long as we can simulate. And then for the processes, we also have, let's say, the basic building blocks could be AR, MA, or full all winters. or a full state space definition. And then we can also compose it or combine them in a very loose meaning of the way. For example, some of the combinations, I would say that concatenation, for example, the ARIMA class is a concatenation in my terminology of AR and MA. So it means that they don't overlap. Like, well, you can have both in the same process. But then we can also compose it, and I will also want to create here to the Adam developers, because I believe they have some, you can run an exponential smoothing with R errors, with R innovations, if I recall correctly. So this is basically the same idea, and we call composition in the mathematical term of the way. So you have white noise, then you compose it with an AR process, and then this is the innovation distribution that comes to your exponential smoothing. And interesting here, there might be some equivalences, right? So maybe you are doing this and it results that it's equivalent to other thing or other of the notable models that we have. But that's another way. And then the infamous model combination, multiplication, etc. And then we can put parameter constraints. We can do XOR, either this process or this other process. So there are different ways of combining. It can basically give us wins in the way of definition. So I have here an example, right? So, well, also you might cringe a little bit, but it's like a sketch of, okay, my specification for a ARIMA process is normal distribution that they get composed by a concatenation of an AR file and an MA file, and then get composed again with just an integration of order 1, for example. And then the estimator for this class, the estimator, you add an unbiased, and you put the trade-off between bias and prediction error. And you add also prediction error as your objective. And then I will throw in, just also to show off, that we can also approximate robustness in the sense of robust estimators, breakdown point of whatever you want. We can also do that, which I think would be a hard problem if you were to estimate. Breakdown in the sense of you can contaminate artificially some part of the time series with any value that you want, and you will still get some reasonable inputs. So yeah, so this is an example. And just to finalize, we can do this model combination, right? The infamous model combination. So we can, with this idea, we can simulate ARIMA, exponential smoothing model combinations, and we can create an estimator for the model combination. Instead of what we tend to do, estimate one, estimate the other, combine them with some weights, we do this. And then just as an idea, when we even if we combine independent AR1s, independent time series of AR1s, we sum them up, we get a long memory process. So if we do this in simulations, we would get an estimator for something that it can be quite complex to grasp, but we can simulate and we can estimate. Just for the interest of time, I will just finish up with the results of this, model combination. Smoothing is 2.94 mesh in the M4 yearly. And if you even the top foundation models, as has been posted in the Giftable Hugging Base space, maintained by Salesforce. The recent one is T-Rex. It is the best one on average. In the M3, you will get this maze error, theta method. It's another foundation model that one is familiar with. Gets better prediction error in this data set. But anyway, there are some limitations. Sorry, I'm always over time. But there are some limitations for this approach. Mainly, there is some computational aspects, but I've been working on improving that. So you can convert train this estimator much faster, so you don't need to wait days or pay some compute budget. You can still do it and get maybe more variety, etc., or depending on the processes, but you can do it. But the main limitation is misspecification, because I don't know, I simulate from some process when the reality doesn't follow that process. I don't know as well what's going to happen, in the sense that least squares, we know that more or less is robust for the exponential family, but or some good properties for the exponential family at large. Here I don't know if I think Gaussian, but then I get Laplacian. I actually don't know how good it's going to work, and it might work well, it might not, but that's kind of the point. And just, this is the final slide. So basically, the idea is that the concept is you can easy to simulate, very hard to estimate, and then we can create new processes. And for this talk, is like I think we should come up with new abstractions of how to define models. I'm particularly interested in new models derived from first principles. I'm thinking, for example, from queuing theory, you can come up with define some process that then has realizations that you can estimate better, etc. So that's it for me.
So, so I'm discussing for this talk. So my first question is about the grammar. Last few slides, and you talk about. So how could we automate the processes? Because in the example of a very beautiful picture that it seems to be that we can fine tune some numbers inside it, like other days there's a trail of 0.9. So how can we?
Yes. So yeah, thanks for the question. So in the sense of I've been doing a little bit of this in the sense that because when you try many experiments, you end up having to refactor and try to do some software engineering. But for example, convex combination is you can do convex combinations very general, very easy to implement, right? So just give me two processes and then just simulate uniformly the weight for combining them. If I have more, I will just simulate weights that sum one. So in that sense, in terms of the number that you put, we can be, if you want to put more information, you can do it, but we can be very uninformative, like, okay, just get uniform weights for the combination. In this, for example, if you want to remove the bias and you want a specific trade-off, that it's up to the analyst. You can try to see the trade-off for a process and think what's your taste for bias, what's your taste for prediction error, and you can also add different metrics for the bias, how you measure bias, etc. So there are many things that we can do, but in terms of the numbers, I would say the principles is most like being uniform, not informative. You can always zoom in something most close to reality. For example, get some empirical distributions from a first parts of the models and then simulate from that distribution that is closer to reality. But in general, in a very general sense of the estimator, maybe in the classic frequency number, you don't want much to be much informative. You just want to cover the full parameter space and then impose properties. Basically, there is also a beautiful equivalence between some properties of the estimators and some basically some prior distributions over the parameters. Sometimes it's very hard to come up with a prior distribution. I think, not sure, but in the minimax estimator, of course, you have a Bayesian equivalence. You have a prior distribution that the Bayesian posterior will give you the minimax estimator. But I don't know for any kind of metric that you would like, error metric, if that's easy to do. But the principle, I would say, from the more frequency point of view, is try to cover the parameter space and try to impose properties in your estimate.
And one more question for me. So, because in the presentation, the estimated result in less biased parameters. And do you see any evidence about the bias, the forecast, whether?
So we can. So basically, I'm not sure if I said it correctly, but if you get the unbiased estimator of the parameters, hopefully you'll get unbiased prediction. But you can also directly minimize the trade-off in the forecast. It's more annoying to do, but it's something that can be done. But usually the bias is for the parameter estimations, but can also.
Okay, so maybe we have two more questions. And yeah,
can you explain this max-min part? Actually, how you set up this theoretical approach?
So let me think. So the principle that we can do here is that we can simulate so much data that you can almost approximate this. Let's imagine, like, let's go back to, I think this is, I didn't include it here, but this is the error versus value of the parameter plot, right? So what we can do, we can simulate so much data here that we can actually approximate almost the true number. So what we can do is penalize deviation. So a minimax estimator will be a flat line here. So we can try to penalize if you derive, the farther you are from a flat line, this is bad, and then you want to make it as low as possible. So you have this trade-off objective. You put some weight. Ideally, you put
You try to win against nature.
Yes, but this is not like generative adversarial networks. This is more like classic optimizer. So it's like I'm not an expert, but they call it high-level optimization. So you can try to set it in this way and do gradient descent on that.
I understood that it looks like a zero-sum game where you just have a Nash equilibrium.
Yeah, so that the Nash equilibrium is the estimator and the on one hand, and the other player is the distribution. The parameter, the prior on the distribution for alpha in this case. So that would be the equilibrium, yes. If you deviate from that, other player will be able to exploit.
But in Maxime, you don't have a Nash equilibrium. You just choose the one that is actually minimizing your time.
Okay.
You go to zero. And zero-sum game, you have a Nash equilibrium.
Okay, yeah. So I might be, so I'll need to think about that. Like what I want to say, the minimax estimate. Yeah, I will, because there is some equivalency with games, but yeah.
I don't really understand why you care about the bias
Oh, yes.
parameters. Like, forecasts are what's important.
Yeah, so that's why I made this.
Parameters, who cares whether they're biased?
Yes. So this is, I was thinking of who can be interested in that. Like, so in some ways, if that's why I made the example of the additive constant, they might be the only thing that you care about in an experiment. Like scientific experiment, let's say you try like a drug and then the observations are correlated in time. You just want to get whether the average or the stationary value of the parameter. So you could rewrite it well. The additive constant is proportional to the long-term forecast, but in a way, it's a simplification. But both, I would say, are relatively equivalent, right? One or the other. But yeah, so the idea is that, yes, in a scientific experiment, I would say that my starting assumption is you care about unbiased of estimator of maybe one of the parameters in your model. Maybe not all parameters, but at least one.
Has to care about the constant, because that's going to affect the level of the forecast.
Yeah, but in this case, I don't know if it's even, it's not forecasting itself, it's more like in time series analysis, you want to find whether the change that you make.
Okay, but I'm coming at this from a forecasting point of view. If I do it up here.
Yes, I was expecting some comments on that, but yeah, this is more in time series analysis.
A related thing is you comment on model misspecification. Every model is misspecification.
Yes. Well, that I'm thinking of if it's a way of thinking, right? We have some assumptions and then we see how we deviate from some assumptions. In this case,
that's sort of the classical statistical.
Yeah. That's
the way I think about model. But I think from a forecasting point of view, that's the wrong way to think.
Yeah. But in this case, it is in my previous comment, the important aspect was most like parameter uncertainty. But in this case, we are always putting some assumptions. And I guess I didn't prepare much for that, but there are always some assumptions. Maybe sometimes we don't know them, but there is always some assumptions. But we can always try to increase the generality of the model class. But yeah, it's given, basically in this case, we are using exponential smoothing. We think that the universe follows that, and then we can get some better calibration based on that. So then we go to reality. That's a different story. But
And I never think the universe follows some model.
yes.
Models of approximation.
Yeah. It's our working assumption just to make some progress. It's not like a strong belief on that. It's basically to get some progress. But I would say that the only thing that I can deliver that maybe not so other people, is the results in, at least in benchmark data. Let's see when it gets to reality. They tend to follow a little bit kind of the theory. So we are lucky in that regard, for example, even though I'm not sure if it happens all the time, but so when I was doing the minimax estimator, it was a bit exotic for me at the beginning. Seeing this curve is like, well, I think that it's working, but this is on real data, and you see that the biggest errors are less likely compared to the other estimator. In this case, it might be that maximum likelihood is when there is white noise in the data, it will correctly detect that there is white noise. When you start moving toward the random walk, then it will think that it's white noise when it isn't. So the errors might be bigger, because like instead of copying the last observation, you will just get the historical average. It tends to be very far away in a random walk. So anyway, it tends to follow a little bit the theory, but this is a tool a thinking tool.
Okay, so we don't have much time, so
Thank you very much.